Yeah, hi everyone. So I'm Damien from Facebook. I'm going to tell you about some joint work with Flavian and Olivier when all of us were at Criteo. So this work is called cost-sensitive learning for utility optimization in online advertising auctions. So the agenda. So I'll first set some context. What do we mean by online advertising auctions and what are we talking about here? Then I'll talk about the offline and online metrics people typically use in these settings. Then that will motivate the idea of utility optimization. And then I will go into our method and I'll conclude with some offline and online results. So here I'm talking about online advertising auctions. So it's not like the typical setting of Facebook or LinkedIn. It's like the display advertising setting when people can see ads on any publisher. So the typical journey is that someone will go to a publisher like the New York Times, and then the New York Times will have like ad slots that they want to sell. So they will contact an RTB platform like Google, and they will say, okay, I have these different slots that I want to sell. Can you please contact people that are interested? Then the RTB platform will contact different bidders like Criteo that represent advertisers, and then each bidder will submit a bid, typically the highest one across all the advertisers they represent, and then the highest bidder would win the auction. And here I would assume a second price auction, meaning that the highest bidder would pay the price corresponding to the bid of the second highest competitor. So that's kind of the context. And then most people, so you can have different types of pricing models in this context. So people can pay for impressions, can pay for clicks, can pay for conversions. But I think what's pretty much uniform in the industry is that advertisers care about deep funnel events, meaning for conversions. And so all the bidders will typically try to optimize for conversion directly so that they can provide as much value as they can to advertisers. So here I will assume that each bidder has like a conversion model, and I will focus on these aspects. So this talk is about how we can make this conversion model using online auctions better than existing state-of-the-art models. And yeah, to give you a bit more context, to be sure like the context is clear, this is kind of the formula for the payoff you typically observe in this type of auctions. So I'll decompose it so that because this notation will come again and again in the talk. So to be sure we get that right. So C here is a cost of winning the auction. And so because I assume second price auction, this corresponds to the second highest bid in the auction. Then I would assume V to be the value of the conversion. So if we have a conversion, so Y corresponds to a binary variable that says if the conversion happens. Then if the conversion happens, we have a payoff of V if we win, because that's the value of the conversion by definition, minus the cost of the conversion, which is C. So the payoff when we win is Y times V minus C. So that's whether the conversion happens times the value of the conversion minus the cost. And this happens only if we win, and we win if the probability of the conversion happening times its value, so P times V, is greater than the second highest competitor, which is C. So that's kind of the payoff when we win, and we don't have any payoff otherwise. And it's interesting to note that, of course, if the conversion doesn't happen, so if Y is 0, then even if we win, we get 0 payoff. Because here I assume that we optimize for conversions, that's what we care about. Okay, so in this context, how can we optimize for conversion models? So one thing to consider first is what are the typical offline and online metrics people use in this area. So again, for online metrics, I think typically like different bidders and different companies would use different values for the online metrics. But I think what's universally true is that you need to weight the conversions because conversions are very different. So because bidder typically represent different advertisers, and even within one advertiser, you can have different types of conversions. So some advertiser can sell both cars and stocks. And then if you think about what you're trying to optimize, if you just sum the total number of conversion, then that's not exactly what the advertisers care about. Because if you get 10 more stocks and 100 more cars, maybe it's better than 10 more stocks, 100 more stocks and 10 more cars, because cars are more expensive. And so I think what's typically used in industry is that people would weight conversion by some flavor of CPA, to represent how much the advertiser care about each conversion, how valuable it is for each person, and that's what people will typically use to weight conversions, to measure the online performance of the system. And then we can go about offline metrics. So then we have the same now we're talking about offline evaluation of the conversion model. So we can use some test sets, some hold-up data, typically like a later day compared to the training data, and we want to measure the performance of the model on this data. So we can use different types of metric. One typically used metric is the mean square error. And here it's important to note that we also weight it by this value V, which is the CPA I was talking about. And why do we do that? So the reason is simple, like because the online metric is weighted by this, we should also reflect that in our offline evaluation to have as strong as a match between offline and online evaluation. And so at Qt we found that the utility metric, I'll try to walk you through that, is very useful to evaluate the performance of conversion models. So if we go back to the payoff from before, so one thing we could use to evaluate our model is to look at the empirical utility. So because we have this in our logs, we have all the payoffs that we had on one impressions. And here this depends on P, right? Like this value depends on P. And P is basically the model itself. So what we can do is actually recompute this value for different models, for different predictions of P's, and see how it affects the empirical utility. So if you only use this payoff, it's not very useful, and it has many drawbacks. One obvious one is that if you over-calibrate, if you bid 10 times more on all one impressions, you would get the same payoff. But that's not really representative of what happens online. Because if you would bid 10 times more online, sometimes someone will bid just below you, and so you'll pay a huge amount of money for almost no payoff. So in practice, that doesn't make sense. So what we proposed in a previous paper from Qt as well is this utility metric, which is basically the payoff. So if you see here, we have y times b minus c, which is exactly the same payoff as we had. But then we don't assume that the cost is constant per impression, but we will put a probability distribution on it, so that's the value of this probability. So that given the cost that we observe in the log, we put a probability distribution for the cost to happen, so that we add some variability to this computation. And so that allows us to compute to estimate the profit that will happen online if we would change the model P without the drawbacks I was mentioning earlier. So for details about this, I would refer to the utility paper. The point I want to make here is that this metric correlates in our experience better with online results than typical classical classification metric. And that's why we care about this. And so then we had the idea, can we optimize for this metric directly? Can we optimize for the utility loss? So which would be the inverse. So I just invert these two terms here. The inverse of the utility metric. But that's a hard problem. So utility is non-convex, and it's not an easy non-convex problem. So there are many people solving non-convex problems in the industry. This one is pretty tough. So we tried many things to try to make this work, but that's pretty difficult. So then we're thinking, because now we have this offline metric, online metrics that are weighted, and we have this metric that we care about, but this is really hard to do. And if you compare to typical state-of-the-art method, then they would rely on the standard log loss. So we have the current log loss, which is pretty far away from the typical metric we care about, and we have this loss, which is what is closer to what we care about, but it's really hard to optimize. So then the idea is that can we try to find a middle ground and to try to optimize something that is easier to optimize but closer to the online and offline metrics of interest. So then we started to look at the connection between the utility loss and the log loss. And so what we do is that we analyze the utility loss from before, and we make two assumptions, three actually. So one thing I didn't mention here is that we need to choose what distribution this probability distribution falls. So here, for this analysis, we assume a log normal distribution, which makes sense based on data. And then, of course, we cannot make a general claim comparing the utility loss to the log loss, because one uses the C, like the cost, and the other one doesn't. So there is no hope to make a general statement about this. But what we do is that we analyze the behavior, like the derivative of the utility loss when C is close to our bid, which happens in practice because auctions tend to be pretty dense, and so the cost that we pay will be close to our bid because there is a lot of competition. So that's the first assumption that we make. And the second one is that we assume conversion probability to be small, which is also true in practice. And then what you can look, so if we assume these two things plus the fact that the probability distribution is a log normal distribution, so there are all the details in the papers, Here, I just want to summarize what you observe in terms of derivatives. And the interesting insight is that the derivatives are actually approximate up to a factor v, which is the value of the conversion, like the CPA from before. And so this motivated us to try to go closer to the utility optimization by weighting the log loss by a weight W, the weight V, sorry. That are the CPA of the conversions. And to maybe to convince you further of this idea, we have also a toy example where we compare two advertisers with two different conversion rates and two different CPAs. And here we have an advertiser with a lower conversion rate but a higher CPA. So to some extent, they should be equivalent because the CR is lower but the conversion is higher. So the conversion of the second one, because CPA is higher, are more valuable. So we should, when we optimize, we should care about this. And so here we have a toy example on these two advertisers, and we look at the optimal point of the utility loss, of the weighted log loss, and the log loss. And we see that the utility is way closer, the weighted log loss is way closer to the utility loss than the normal log loss. It's not super easy to see here, but basically this point is way on the right compared to this one. Sorry, this one is on the right compared to this one, which is closer to the utility one. So moving forward, so we propose to optimize for the weighted log loss to improve our bidder performance. And here just a side note, so there are many different ways you can add that in your optimization. Here we rely on a batch method, we rely on LBFGS for the optimization. And so it's really easy to add the weight because you can simply multiply your gradient by the weight. In case you use LGD, so it's a bit more tricky because you cannot just do that. And you have to rely on maybe approximate method. There are some references about this in the paper as well. And then one aspect we do need to be careful about is the impact it has on regularization, because now in our previous model, like the previous logistic regression model, we have a lambda that controls the regularization, and here I assume like L2 regularization, but we have to change this value and taking the weights into account. So we propose this heuristic to kind of automatically compute it, and I'll go into some results showing that this is actually a reasonable heuristic. So now the offline online results. So we tried this first on, so we tried both on internal data at Criteo, obviously, but also on the public data set for the paper. And here we'll first go about like the offline result on this public data set, noting that, note that we also had similar result offline at Criteo, although this is not part of the paper. And then I'll talk about online results. So the first types of offline results, we were interested in what types of weight do we need, because I think it's pretty well known that if your weights are too high, then you can overfit the weight, and then you don't really have the effect you care about, because then you would overfit the big advertisers, the one with big CPAs, and you wouldn't be representative as of the whole distribution either, which is not exactly what you want to achieve. And here we see that putting the weights directly is better on two of our, so as metrics we use the mean square from before and two utility method. So we believe more in the utility ones, and so we see that one of the utilities is better with the CPA weights directly, and another one is better with square root of the weights. So we see that the point here is that using the weight directly is okay, but maybe it would be safer to use like square root of the weights to avoid overfitting on the big CPAs. Then we looked at our heuristic, so we tried to look at the lambda for heuristic and then at some values around it. So we see that the optimal value is not the heuristic, but the value is pretty much the same. So we see that the heuristic is 0.3% plus minus 0.04, and the best one would be 0.34. So it's really close, and yeah, it's really close, not even statistic. So we are pretty happy about the heuristic we propose. And then the last set of offline results are about high versus low CPA. So because here we are really interested about improving the performance on high CPA. They have less data, so they would be fit less well on the data typically. So we try to see if, as we would assume, the performance improves for them. And we see that it is the case that the utility is improved more. So you see like 1.7 on the high CPA compared to the global one, which is only 0.32. And we see this is even more true. Yeah, if you put high CPA and high CPA low sales, so the ones that have even less data, it improves even more. Yeah, and then we did online A/B test. So we took our conversion model, we put the system in place, and then we A/B tested on like 1 billion displays on worldwide retail traffic, and we observed that the change resulted in plus 2% lift in ROI, which is pretty significant compared to changes you typically observe in the industry, and that we tended to observe at Criteo as well. And to give you slightly more insight, so we observed significant savings in display costs and increase in sales performance, especially for the campaigns with high CPA, as you would assume. And to conclude, so we show that the weighted log loss allows to get closer to the offline-online metrics of interest in the context of online advertising auctions, and that it allows to get closer to utility optimization without the convexity problems. Thank you.